All right, it's time to add, if you will, pun intended, some rules that we can use to calculate more complicated probabilities for more complicated events. And in this section, we're going to look at some of the additive rules that we can use. And we've got Theorem 2.7 associated in our text that we'll start out with that talks about the probability of the union of two events, A or B. Now, the union of two events, the probability is not necessarily just the sum of the separate probabilities of the events A and B. We also need to make sure we add any probability of the intersection there because we could potentially be double counting. All right. And this can be seen nicely if we take a look at a Venn diagram. Just to show that how this works. This can be seen in a Venn diagram. Let's go ahead and take a look at a Venn diagram here, trying to illustrate how the left-hand side is equal to the right-hand side of this theorem. So let's take our two events, A and B. A and B. Now, the probability that we want here is the probability of A or B. So we want to be calculating whatever all this probability is. So we'll just try to shade that in real quick. Give it a rough. If I had a more fancy application here, right, I could just do fill or something like that. Drop a paint bucket on it. Good enough. There we go. That's the probability we want. So is this equal to the probability of A plus the probability of B minus the intersection, right? Well, take a look at this. You've got just the probability of A. Let's make this slightly more circular. So here we go. Just the probability of A. Okay. And if we add to this the probability of B, what happened is you've double counted the intersection region, right? You've double counted that intersection region here, right? You've double counted A intersect B is in both A and B, right? You've double counted the intersection region, so we're going to subtract the probability of A intersect B. So we're going to subtract just that intersection off. So we are just going to subtract off this region that we've double counted right here. Double counted there, okay? Now, this is nice when they are mutually exclusive, right? Because if A and B are disjoint or mutually exclusive events, then the intersection is equal to 0, and it would just be P of A plus P of B, right? So they're mutually exclusive. The intersection is 0. It's not that that really changes this formula, but it just simplifies it a little bit because this last term just zeroes out. Let's dive into an example using this. An airport security has 2 checkpoints. Let's let A be the event the first checkpoint is busy. I'm going to have capital B be the event that the second checkpoint is busy. Okay, so let's assume that we know some things here. We are given that P of A is 0.2, 0.2. Probability of B is 0.3, and the probability of A intersect B is 0.06. Find the probability that at least one of the checkpoints is busy. At least one of the checkpoints is busy. At least one of the checkpoints is busy. All right. So the key thing here, this problem does seem a little bit trivial given that we just talked about theorem 2.7, but the key thing here is if you encounter this problem out in the wild, that we are looking at this phrasing here, probability that at least one of the checkpoints is busy, at least one. So how do we interpret that? That could be A or B or both, right? At least one, A or B or both. That is the union A or B. And so we want the probability then that A or B are busy. So this is just a direct application then of the theorem. So this is P of A plus P of B minus the intersection if there is any. And in this question, we're given all the probabilities we need. P of A is 0.2. P of B is 0.3. And their intersection sure does exist. That is 0.06. And we run those numbers through a calculator. And we see that it is 0.44 or 44%. 44%. Okay. Quick follow-up pop quiz. Are A and B mutually exclusive events? Are A and B mutually exclusive events? The answer is no, they are not. They are not mutually exclusive because their intersection is non-empty. We have a positive probability at their intersection. If they were mutually exclusive, the intersection would be 0. All right. Okay. Let's think back a little bit to a few videos ago and recall that a collection of n events is called a partition. Remember the word partition. A collection of n events is called a partition of S if they are mutually exclusive. If they are mutually exclusive and the union of all of the events gives you the whole set, and A1, union A2, union A3, yada, yada, yada. If we have n events, the union of all of them gives us the sample space. They are mutually exclusive and the union gives you the sample space. Okay, so just related to a partition specifically, we're going to talk about what's associated in our text as corollary 2.3. Corollary is sort of like a mini follow-up from a theorem. Not quite strong enough to earn its own theorem word, but still important nonetheless. If we have these events, A1, A2, yada, 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 AN, that are a partition, they form a partition of S. That form a partition of S. Then, because they're mutually exclusive, we can extend this idea of the probability of the union of two events, or more actually, very generically. Because they're mutually exclusive, they form a partition, so they're mutually exclusive. The intersection of any of these is empty. And so the probability of the union of all of these is just the probability of the first event plus the probability of the second event, so on and so forth. Just add the separate probabilities, and we don't need to worry about any intersection. The sum of all of these will sum up to 1. Okay? If these events are not a partition of S, right, then this probability right here gets a lot more complicated because you have multiple overlaps you could potentially deal with. Think, for example, extending this Venn diagram scenario to 4, 5, or 6 different events, 4, 5, 6 overlapping circles, and trying to account for all of those extra intersections that you're maybe double or triple or quadruple counting. But in the case of a partition, it's quite nice. Let's dive into one more example here. If the probabilities are, respectively, 0.09, I've got a list of probabilities here. 0.09, 0.15, 0.21, and 0.23, that a person purchasing a new car, purchasing a new car, chooses the color green, capital G for green, white, capital W for white, red, capital R for red, or blue, capital B for blue. So if the probabilities are respectively 0.09, 0.15, 0.21, and 0.23, respectively means these probabilities get associated with the items in the list. So the 0.09 is the first probability. That is for the first item in the list, the color green. 0.15 goes with white. 0.21 is the probability that they get red. 0.23 then would be the probability that it's blue. What is the probability that a buyer will purchase one of these colors? One of these colors. Well, we want the probability that they get a green one, or a white one, or a red one, or a blue one. Probability G, or union W, union R, union B for our colors here. What is the probability? So this is the union of more than one event. Let's think about this here. It looks like they can get a green car, a white car, a red car, or a blue car. Seems implied that you can't get a green and a white car, right? Or that we can't get a red and a blue car. And so these color choices looks like they are all mutually exclusive. And so because they're mutually exclusive, we don't need to worry about any intersections. And so we can just add up the individual probabilities. Right? Because mutually exclusive or disjoint. Mutually exclusive events. Because they're mutually exclusive. And so given in the problem, we have 0.09 plus 0.15 plus 0.21 plus 0.23. So we add up the probabilities there. 68% chance then based on this. Just a 68% chance, all right? So when the events are mutually exclusive, these union probability questions are actually quite nice. Are these events, follow question, do these events form a partition then? Are these events a partition? Well, take a look at your notes. What do we have in core layer 2.3? They are a partition of S. Then the probability of the union of the events sums to 1. These do not sum to 1. No, They are mutually exclusive, but they don't sum to 1, so it's not a partition. The probabilities do not sum to 1. Not a partition. Mutually exclusive, but not a partition. Okay. You might be asking yourself then, well, hey, Aaron, hold on. What happens if these aren't mutually exclusive? Are we just really that out of luck if I want the probability of G, union W, union R, union B, if they're not mutually exclusive? We can tackle that. That, in our text, would be Theorem 2.8. Theorem 2.8 talks about how we can look at the union of 3 events separately. What is this equal to in general? Whether or not they are mutually exclusive? That is a topic that we will leave to the next video. Time to take a break. Let's pause and gather ourselves, grab a drink of water, go to the bathroom, and then come back, and then we'll look at the union of 3 events and discuss that scenario. We will see you in the next video.